What's up, guys? I'm Mohit K. Kashyap from SVC College of Engineering, which is in Vidyanagar Cross. Today, I'm going to teach you guys about characteristics and quality attributes of an embedded system. So, this is a very really a basic topic. So, it's going to be really easy, and we're gonna finish it real quick. So, let's move on to the next slide. So, characteristics of embedded systems. So embedded system possesses certain specific characteristics. These characteristics are unique to each embedded system. Some of the important characteristics of embedded system are application and domain specific, reactive and real time, operates in harsh conditions, distributed, small size and weight, and power concerns. So what I'm trying to say is, so each embedded system, for example, if I had to say in a local language, each embedded system or chip has its own specific characteristic. So today we are going to just study about all the specific characteristics. So moving on to our next slide. So let's start with our first point, which is application and domain specific. So I'll just read you the points I have mentioned in the PPT. Then I'll explain it to you later. Okay. Each embedded system has certain functions to perform, and they are developed in such a manner to do the intended functions only. They cannot be used for any other purpose. So I've given two examples in the examples below. For example, the embedded control unit of microwave oven cannot be replaced with an air conditioner's embedded control unit because the embedded control units of microwave oven and air conditioner are specifically designed to perform certain specific tasks. Also, an embedded control unit developed for a particular domain, say telecom, cannot be replaced with another control unit designed to serve another domain like consumer electronics. So, if I want to give an example on this topic, so let's consider okay, an engineer and a doctor. Okay, an engineer cannot perform the activities of a doctor. An engineer has studied a certain course to do only engineering things. Likewise, a doctor cannot perform all the specific tasks of an engineer, okay, because he has studied something different. So they are domain specific. That's how we categorize them, okay. They are domain specific, like engineers, artists, then doctors, etc, etc, etc. Likewise, even the embedded systems are domain specific. A certain embedded systems used in washing machine cannot be used in air conditioner. Embedded systems used in air conditioners cannot be used in fridge. So though it all appears to be the same, but it has got some different functions. So moving on to the next slide. So let's go to a second point, which is reactive and real time. So embedded systems are in constant interaction with the real world through sensors and user defined input devices which are connected to the input port of the system. Any changes happening in the real world, which is called an event, okay, are captured by sensors or input devices in real time, and the control or algorithm running inside the unit reacts in a designed manner to bring the controlled output variables to the desired level. So for example, the way we predict weathers, predict natural disasters, so these are all done by embedded systems because they are like interact with the environment. So that's how we get to know the weather and all the natural calamities which might occur in the future beforehand. Okay, embedded systems produce changes in output in response to the changes in the input. Okay, has the input right, like it has the ability to adapt to the its environment. Okay, as the input changes, it also changes its output. So they're generally referred as reactive systems. So moving on to our next slide. So real-time system operation means the timing behavior of the system should be deterministic. Okay, the system should respond to requests or tasks in a known amount of time. A real-time system should not miss any deadlines for tasks or operations. It is not necessary that all embedded systems should be real-time in operations. So it is not necessary. Okay, Embedded systems applications are systems which are mission critical, like flight control systems, anti-lock braking systems, etc. are examples of, they're like real-time systems. Okay, and so our third point is operates in harsh environment. Okay, the environment in which the embedded system deployed may be a dusty one or a high temperature zone or an area subject to vibrations and shock. Systems placed in such areas should be capable to withstand all these adverse operating conditions. The design should take care of the operating conditions of the area where the system is going to implement. For example, if the system needs to be developed in a high temperature zone like Thar Desert, then all the components used in the system should be of high temperature grade. Like it shouldn't like the the heat withstanding capacity of the embedded system should be like very high. Okay, then also proper shock absorption techniques should be provided to systems which are going to be commissioned in places subject to high shock. Power supply fluctuations, corrosion, and component aging, etc. are the other factors that need to be taken into consideration for embedded systems to work in harsh environment. Our fourth point is distributed. The term distributed means that embedded systems may be a part of larger systems. So many number of such distributed embedded systems form a single large embedded control unit. For example, an automatic vending machine. The vending machine which you see nowadays in the mall or maybe in your college or school. So we are talking about that vending machine. Okay, it contains a card reader. It contains a card reader, a vending unit, etc. Each of them are independent embedded units, but they work together to perform the overall vending function. Another example is the automatic teller machine, which we all know is an ATM machine. So it contains a card reader embedded unit responsible for reading and validating the user's ATM card. Transaction unit for performing transactions. A currency counter for dispatching vending currency to the authorized person, and a printer unit for printing the transaction details. We can visualize these as an independent embedded systems, but they work together to achieve a common goal. So what I'm trying to tell you is embedded systems, like they all work like a team. Okay, just like team India in cricket. Okay, so each embedded systems has got its own role. Okay, but they work separately, but they all work for they all work to achieve a common goal. That's what I'm trying to say. They work separately and independently, but they all work together towards a common goal. So another typical example of a distributed embedded system is the supervisory control amplifier data acquisition system used in control and instrumentation applications, which are physically distributed individual embedded control units connected to a supervisory module. Okay, so moving on to our next slide. The next point is small weight and size. Product aesthetics is an important factor in choosing a product. For example, when you plan to buy a new mobile phone, you may make a comparative study on the pros and cons of the products available in the market. Differently, the product aesthetics like size, weight, shape, and style will be one of the deciding factors to choose a product. People believe in the phrase small is beautiful. Okay. So moreover, it is convenient to handle a compact device at a bulky product. Okay. In embedded domain also, compactness is a significant deciding fact. Most of the application demand small sized and low weight products. We Most of the application demand small size because it saves them a lot of space. So it makes it more efficient. It saves them a lot of space, easy to carry, and as we all know, small is beautiful. So moving on to the next slide. The last point of this topic is power concern. Power management is another important factor that needs to be considered in designing embedded systems. Embedded systems should be designed in such a way as to minimize the heat dissipation of the system. The production of high amount of heat demands cooling requirements like cooling fans, which in turn occupies additional space and make the system bulky. As we all know that in the recent laptops nowadays, like the gaming laptops, so there are a lot of heating issues. So they're providing large fans for to reduce the heating and improve the cooling throughout the laptop. So you might take that as an example and select the design according to the low power components like low dropout regulators and control processors with power saving modes. Also, power management is a critical constraint in battery operated application. The more the power consumption, the less is the battery life. For example, you might see iPhones have a comparatively less battery life compared to other phones, so you might take that as an example. So moving on to our next slide. So in this slide, we are going to discuss about the quality attributes of an embedded systems. Quality attributes are non-functional requirements that need to be documented properly in a system design. If the quality attributes are more concrete and measurable, it will give a positive impact on the system development process and in the end product. The quality attributes are classified into two types, that are operational quality of attributes and non-operational quality attributes. So in the next slide, we are going to discuss in detail about the operational and non-operational quality attributes. So what is an operational quality attribute? The operational quality attributes represent the relevant quality attributes related to the embedded system when it is in the operation mode or online mode. The important operational quality attributes are response, throughput, reliability, maintainability, security, and safety. So let me explain you about all these points in detail in the next slide. Okay. So response is simply the measure of quickness of the system, how fast the system responds to the inputs. It's all about that. It gives an idea about how fast the system is tracking the changes in input variables. Most of the embedded systems demand fast response, which should be almost real time. For example, embedded system deployed in flight control applications should respond in a real time manner. Any response delay in the system will create potential damage to safety of the flight as well as the passengers. It is not necessary that all embedded systems should be real-time in response. For example, the response time requirement for an electronic toy is not it's not at all time critical. There is no specific deadline that this system should respond within this particular timeline. So you guys understood, right? So moving on to the next slide. So next point is throughput. Throughput deals with the efficiency of the system. Throughput can be defined as the rate of production or operation of the defined process over a stated period of time. The rates can be expressed in terms of units of products, batches of products, or any other meaningful measurements. In the case of a card reader, throughput means how many transactions the reader can perform in a minute or an hour or in a day. Throughput is generally measured in terms of benchmarks. Okay, a benchmark is a reference point by which something can be measured, just like an SI unit you might consider. Okay, benchmark can be a set of performance criteria that a product is expected to meet or a standard product that can be used for comparing other products the same product line. Just like just like an SI unit, okay? Just like an SI unit. So, so third point is reliability, okay? Reliability is a measure of how much percentage you can rely upon the proper functioning of the system, or what is the percentage susceptibility of the systems to failures, okay? It's like how better can you trust the system, okay, to get your job done, or yeah, or to trust on your safety, okay. So system reliability is defined using two terms, okay. The mean time between failures, MTBF, gives the frequency of failures in hours, weeks, or months. Mean time to repair specifies how long the system is allowed to be out of order following a failure. For an embedded system with critical application need, it should be of the order of minutes. So moving on to the next slide. So fourth point is maintainability. Maintainability deals with support and maintenance to the end user or client in case of technical issues and product failures or on the basis of a routine system checkup. Reliability and maintainability are considered as two complementary disciplines. A more reliable system means a system with less corrective maintainability requirements and vice versa. Maintainability can be broadly classified into two categories: scheduled or periodic maintenance and maintenance to expected failures. The remaining 2 points are security and safety. Security and safety like go hand in hand, okay? Okay, to trust embedded systems, it needs to be secure, and we need to safeguard the embedded systems. Okay, so that's the last 2 points. Thank you for watching this video. I hope you guys are doing really well. Thank you guys. Signing off. Bye. Good night, guys.